Okay, so again, I welcome all of you to this platform of Thermal Engineering MEC 551. We have already started with refrigeration cycle. Okay, hopefully today we can complete this slide and then immediately we'll start solving questions. Okay, and last time I ended somewhere around here. Okay, so let us give the overview of what we discussed last time. We did define what a refrigeration cycle is and what a heat pump is. And basically, a refrigerator or a refrigeration system is a device, okay, that takes heat from a refrigeration compartment at a lower temperature and transfer the heat to a high temperature reservoir, means into the condenser. And this is achieved by means of what we call a compressor. So without a compressor, there is no way the refrigerator will be able to function correctly. And the desired output for all refrigerators is the QL. That is the amount of energy that is able to be removed from the refrigeration space. Okay, so and then we define the performance criteria for the refrigeration cycle, in which we mentioned that the COP for a refrigerator is given by the desired output, which is the QL, divided by the required input. The required input is the work input to the compressor. And this can also be written in terms of 1 minus QL divided by QH. And for a reversible refrigerator, we can also say that QL, the ratio of QL divided by QH is given by TL divided by TH. Hence, we can define the COP for a reversible refrigerator. Okay, reversible to be equal to 1 minus TL divided by TH. So take note of this equation. And then we also did discuss the heat pump. So the heat pump basically is also, it has a similar features like a refrigerator, but the difference is that for a heat pump, the desired output is always the heat that is emitted at a higher temperature. Okay, so it means that QH is the desired output for a heat pump. Okay, so today we're going to look at and then yes, we also mentioned about the reverse refrigeration cycle. Mentioned that the reverse refrigeration cycle has so many weaknesses. Okay, it cannot be theoretically or practically be implemented because of the fact that in the reverse Carnot refrigeration cycle, let's see, yes, so you see the compressor, this particular compressor, the fluid that enters the compressor at state 1, if you refer to the TS diagram, the fluid is at the saturated liquid vapor mixture. So this is not desirable for the compressor. The moment you feed the compressor with this fluid, then the compressor will collapse. There will be cavitation. It will be destroyed because the compressor is only manufactured or is only used to compress a compressible fluid such as gas or superheated fluid or saturated vapor fluid. You understand me? So we have to make a modification on this particular features of the reverse Carnot cycle. So what is the modification? The modification is that instead of allowing the fluid to enter at saturated liquid vapor mixture, the state, okay, the fluid is continuously heated until it exists at the saturated vapor state. So that eventually the modification TS diagram for the refrigeration cycle behaves like this. This is the features. So the fluid enters now at state 1 and goes on up to the superheated state at state 2. If you compare to the reverse refrigeration cycle, the fluid is compressed immediately to the saturated vapor state. Okay, so then again, one of the weakness is that here we have a turbine. This turbine, the fluid that enters the turbine at state 3, this fluid is at the saturated liquid state. So it means that if you feed a turbine with a saturated liquid, the work output, this W work output, will be almost equal to 0. So it's just like you are pouring water into a turbine, and the work output will not be any reasonable work output. So for this reason, we kick out the turbine, and then we replace the turbine by means of what we call a throttle valve. Throttle valve, throttle valve. So a throttle valve is used to replace the turbine, and a throttle valve will be able to use and perform even a better function compared with the turbine. Okay, so now this state 3, in which we cool the fluid in the condenser from state 2 to state 3, the fluid is continuously cooled down. It means heat is rejected. You see, if you put your hand behind your refrigeration, you'll see that hot air is coming out. This is the hot air. So it means the condenser is doing its job. So it means the refrigerant is being cooled down to the saturated liquid state. Okay, so then at this state 3, the fluid is throttled. So it's throttled like this. It goes on. So this is the throttle process from state 3 back to state 4. Okay, so this cycle now is what we refer to as the vapor compression refrigeration cycle. Vapor compression refrigeration cycle. You understand me? So a modification of this cycle gives us what we call the vapor compression refrigeration cycle. Okay, so what is the classical difference? Here, the fluid enters at the saturated vapor state. Here, the fluid enters at saturated liquid vapor mixture. You understand me? And here, the fluid exits the compressor at saturated vapor. But here, the fluid exits the compressor at what? Superheated vapor state. And then it is here, the fluid is cooled down at constant temperature, TH. But here, the fluid is cooled at constant pressure. So this is the P diagram. So this is the constant pressure line. Let's say this is P1, this is P2, or let's say this is P1 and this is P2. Okay, so the fluid is cooled down at constant pressure, but at varying temperature. You understand me? Like this. Okay, so that was the summary of what we did last week. So today we will look. We have also defined what these other components of the refrigerators are. Now, here, the schematic diagram for the vapor compression refrigeration cycle is given by this. So this is no more reverse Carnot cycle. This is the vapor compression cycle. So we have the compressor, which is this, and then we have the evaporator, okay, and then we have the condenser here. So now you see the turbine is being replaced by an expansion valve, okay. So this is what we call a vapor compression refrigeration cycle, all right. So now state 1 to 2. State 1 to 2 is isentropic compression. If I draw the TS diagram, let's see, yes, this is the TS diagram for this cycle. So the TS diagram is this. Maybe I should draw it over here so then you see very clearly. So this is a TS diagram for this cycle. Okay, so I hope you have experienced, you have not forgotten your thermodynamics okay, regarding the interpretation of these TS diagrams. So this is state 1. State 1 to 2 is what we call isentropic compression. So the word isentropic, I think I have explained last time. So when we say isentropic, means constant entropy. You understand? So when a fluid is being or a system is undergoing a change of state from state 1 to state 2, in which the entropies, okay, between the two states is the same, then we say the process is what isentropic process, because this state 2, S1 is the same as S2. So it's an isentropic process. So what is the significance of this isentropic process? It means it's a reversible cycle. You understand me? All reversible cycles are isentropic processes in this way. Okay? Then again, we have, yes, so the fluid enters the compressor at the point where x equals to 1.0. Okay, so now, and 2 to 3, heat is rejected from the refrigerant at constant pressure. So this is the constant pressure line. So this is P1, this is P2, constant pressure line. Okay, then the throttle process to two-phase mixture in the expansion valve. So the expansion valve is such a way that there is always increase in entropy. You see, that's why it goes like this. So this is 3, this is 4. So this implies that S3, okay, is not equal to S4. In other words, S4 is greater than S3 because there is increase in entropy between state 1 and state 2. And it is true. You understand me? So because here we have the fluid which is at the saturated liquid state, and this fluid which is saturated liquid vapor mixture, then because of this two-phase fluid, the entropy of the fluid is said to increase in this way. Okay, so this is the clear diagram for the ideal vapor refrigeration cycle. So these are the various features for the pH diagram. Okay, I've told you that the pH diagram, this is the what do you call it? The constant, this is the saturation lines, okay, for along the pH diagram. Then we have state 1 somewhere here. So this is state 1. The fluid is compressed in the compressor from state 1 all the way up to state 2. So you see that here there is increase. So be careful. This is pre-pH. So pressure and entropy diagram. This is different from TS diagram. So TS diagram is this. So TS diagram, in the TS diagram we have this. Let's make a comparison. In the TS diagram, S1, this is state 1, this is state 2. S1 equals to S2. But on the pH diagram, okay, H1 is not equal to H2. In other words, H2 is greater than H1. And it's true because there is increase in temperature. Whenever temperature increases, the enthalpy of the fluid increases also. Okay, so, and then the fluid is cooled down from state 2 up to state 3. So, but again, this is done at constant pressure. So this is constant pressure. Constant pressure is this. And then finally, we have the expansion. So expansion also, now, the enthalpy between the two phases, H3, is always equals to H4. And this is valid for all throttling processes. Throttling processes. You understand me? Meaning the expansion valves. Okay? So now, let us look at some various definitions. When you say refrigeration effect, sometimes you can be asked to determine the refrigeration effect, or you can be told that a refrigerant is used to a refrigeration cycle is being operated okay, and such a way that you are being asked to determine the refrigeration effect. Refrigeration effect means that they want you to calculate the value for QL, okay, in the specific form in kilojoules per kilogram. Okay, so when we say refrigeration effect, it means we want you to determine the cooling load. Okay, so the amount of energy which is taken away from the refrigerated space. Okay, so similarly, when we say refrigeration load, it means QL. QL is the refrigeration load, and this is in kilowatt. Okay, and then the energy balance, if you want to look at the energy balance for the heat input side. So if you establish the first law of thermodynamics, okay, if we take, for example, the Q in, yes, Q in is, if you go to the diagram, Q in is this. This is our Q in. So if we clearly, let's see, look at this energy balance. So our Q in will look like this. Let's say if this is my evaporator, okay? So this is the fluid coming from state 4, and it leaves and enters at state 1. Okay, so here we have Q1, sorry, Q in. This is Q in. All right. So if the enthalpy at state 4, assuming this is given by H4, and the enthalpy at state 1 is given by H1. From energy balance, this first law of thermodynamics, okay, tells us that the net heat added to a system minus the net work should be equal to mass flow rate times the change in the enthalpy between the two states plus the kinetic energy term, this is kinetic energy terms, plus the potential energy terms. But again, for all, control volume systems, we always assume that the change in kinetic and potential energy terms are always equals to 0. So this goes out of the equation immediately. Okay, so and then also, if you look at this diagram, there is nothing like W net. There is no work input. We only have fluid coming in, fluid going out, and then we have heat coming in into the system. So it means the W net also equals to 0. So eventually we'll be left with Q net, okay, which is equal to mass flow rate H2 minus H1. So here H2 is the same as the H4. You understand? So and then H1 is H1 like this. Okay, so I'm very sorry. So and this particular one will be, let's see over here. So we have H2 minus, this is the final enthalpy minus the initial enthalpy. Okay, so initial enthalpy, we can, this is given by H1, H4. Okay, and then the final enthalpy, this one is H2. Okay, so let's remove all this confusion from here. If we do this correctly, we will have mass flow rate of the fluid entering minus mass flow rate of the fluid that is leaving the system. So eventually we will have, let's see over here, Q net equals to mass flow rate. Then we will have H2 over here. Again, this is referring to H1. That's the final enthalpy. Okay, so H1 minus H4 like this. Okay, so and this is the initial, we are taking this is the initial fluid that is entering. And then the final fluid, this is state 2, which is leaving. You understand me? So this now refers to H1, this refers to H2, like this, if you go by this particular equation. Okay, so whichever way you want to write it, The only thing is that just take the notation. Okay, so it could be, we could write it also Q net equals to mass flow rate H1 minus H4. Okay, so it's the same thing. Or according to this particular equation, H2, which is the final enthalpy, minus the initial enthalpy. Okay, so now here where M dot is the mass flow rate of the refrigerant. So in this equation, M dot is the mass flow rate of the refrigerant. And then the heat transfer rate is referred to as the refrigeration capacity. And the capacity is normally expressed in kilowatts. Okay, so now another commonly used unit for the refrigeration capacity is the tons of refrigeration. But 1 ton of refrigeration equals to 211 kilojoules per minute. Take note of this. It's very, very important. Sometimes you can be asked to calculate the refrigeration capacity in tons of the refrigeration. Okay, so 1 ton of refrigeration should be equal to 211 kilojoules per minute. Okay, so then the plant capacity up to 50 tons of refrigeration are usually considered as small capacity, whereas 50 to 250 tons of refrigeration, okay, as medium capacity, and over 250, these are large capacity. So normally these are in the malls or supermarket where they have large cold house, then they, what do you call it? They are operated based on this 250 tons of refrigeration. Okay, so now let us look at the energy balance for the compressor. So in the compressor, let's see over here, the compressor is like this. So this is the compressor. Okay, so the fluid enters the compressor at state 1, and then it exits at state 2. At state 2. And here we have W in for the compressor. Okay, so one technique I'll tell you is that, you see over here, if you know the energy of a flowing fluid that enters the refrigerator, okay, is equal, that enters the compressor is given by mass flow rate of the refrigerant at state 1, M1, times the enthalpy H1. And similarly, E2 equals to M2 times H2. So if you want to establish the energy balance without necessarily writing all this long equation, all that you need to do is that total amount of energy in should be equal to total amount of energy at the exit. So the amount of energy inlet, we have E1, which is this, plus W in. So we have E1 plus W in should be equal to E2. You see? So now what is this E1? E1 is nothing. It is M1 H1 plus W in equals to M2 H2. So if you want to make W in the subject of the relation, you will have W in equals to M2 H2 minus M1 H1. Now, all control volume systems are said to be at steady state. Steady state. Steady state. And at steady state condition, mass flow rate M1 equals to M2 equals to M3 equals to M4 equals to M. Okay, so the mass flow rate means that the mass flow rate throughout the refrigeration cycle remains the same. It doesn't change. Okay, so if that is the case, then I'll say M into bracket H2 minus H1. And that's equals to my W in. All right? So this is very, very important. So now, let us see. For the Q out from the condenser. So the condenser is such a way that we have Q out. Okay, whereas here we have, this is E what? So this is E2, which is given by M2H2. And finally here we have we have E. So E3 energy at state 3 equals to M3H3. So again, if we establish the energy balance for this, it is going to give us the total amount of energy input. It is going to give me E2 should be equal to Q out plus what? E3. What is E2? E2 is M2H2. Then I'll have Q out plus M3H3. Same thing, steady state M2 equals to M3. So eventually, I'll have Q out equals to the change in enthalpy, mass flow rate. So H3 minus H2. You understand? So this is very clear. So next is the throttle valve. So in the throttle valve, you see, this is the throttle valve, expansion valve. The fluid enters the throttle valve. This is state 3, and then it exits. Again, this is state 4. You understand? So here we have energy in E3 equals to M3H3. Here we have E4 equals to M4H4. You understand? Like this. So here there is no heat transfer. The throttle valve or the expansion valve, there is no energy transfer in and out of the system. We only have mass in, mass out. You understand? So now, by virtue of this, we are going to write the energy balance for this. So total amount of energy in should be equal to total amount of energy outlet. So eventually we'll have M3H3 equals to M4H4. Now M3 is the same as M4. So that this and this will cancel out. So we have H3 equals to H4. So all the time, whenever you have a throttle valve or expansion valve, then the enthalpy between the two states should be the same. Okay? So now we define the coefficient of performance for the refrigeration cycle equals to the cooling effect divided by the work input. So now we express it in terms of the change in their enthalpies. So that is H1 minus H4 divided by H2 minus H1. Okay? So later on, we will look at these particular questions. Okay? Now, the solution is also over there, but I will discuss these questions later on. Now, let us look at actual, okay, or irreversible cycles. Actual cycles in the refrigeration systems or irreversible cycles. Okay, so first we look at case 1, means adiabatic irreversible compression. Okay, so the word adiabatic means that there is no heat transfer in and out of the system. You understand me? So now, one thing we need to know. Yes, so this will lead us to the definition of isentropic efficiency. You see, if we have two compressors, one is reversible and the other one is irreversible compressor. The reversible compressor is going to behave such a way that it's, the compression is going to follow this line, the thick line, from state 1 up to state 2s. Whereas the irreversible one, so this is the irreversible compression. Because why is it irreversible compression? Here S1 is not equals to S2. Okay, S2 is greater than S1. But this one, this particular one, the thick line, this is a reversible. Why is it reversible? Because S1 is the same as S2S. You understand? So the change in entropy between the two states is the same. You understand? So this is very, very clear. So that if you want to define the relationship between a reversible compressor and irreversible compressor, assuming that the work input to this compressor, irreversible compressor, is given by WA. And the work input for the reversible compressor is given by WS. The ratio of these two, you see, here we're going to have WA is going to be greater than WS. Why? Because of the fact that it has to overcome irreversibilities. Irreversibilities such as compression, there will be pressure changes, there will be heat loss, there will be friction, especially friction. Friction plays a very large role in the irreversibility of a system. So this is very, very important to know. You understand me? So the major or the main causes of irreversibility of a system is friction. You understand me? High friction means what do you call it? The compressor will not be able to have enough power. So you have to supply more work for it to turn or compress the fluid. And by means of this, it has to consume more energy. You understand me? So that we define a new parameter called isentropic efficiency. And this isentropic efficiency is defined as isentropic efficiency for a compressor is defined as WS, which is the smaller one, divided by WA. And what is this WS divided by? So again, WS is equal to the change in enthalpy between state 2S, so that gives us H2S minus H1 divided by H2 minus what? H1. Okay, so this is very, very important. In fact, in your thermal engineering, if there should be any questions will be revolving around isentropic efficiency of a system. Okay, so again, we'll come to these questions later on. Now, this is now case 2 for the actual refrigeration cycle. So when we say actual, you see, the word actual means in actual cases or practical life situation, all systems are irreversible because there is no way you can do away with the heat losses, the friction, pressure losses, and so on. Okay, like that. So, and actual cases are their characteristics is like that. That there are so many losses which eventually increases the energy consumption of such compressors. So now the second case is like this: the superheated condition at the evaporator exit, which differs from the saturated vapor condition. So here you see in the actual or in the previous refrigeration cycle, our fluid compression started from here, from the saturated liquid state, saturated vapor state. So, but you see that it has pushed a little bit into the superheated state. And this is for real life situation. In all real life situation, the fluid has to be enter the compressor at a superheated state so that we are 100% sure that the fluid that enters the compressor is always at a gaseous state. You understand me? Okay, so it means that there is increase in temperature. Okay, so if you compare the theoretical situation and the actual situation, there is a small temperature difference, which is this. Similarly, on the pH diagram, there will be increase in entropy, increase in enthalpy in this situation like this. Okay, so this is the saturation point, saturated liquid state, saturated vapor state, and then since there is increase in temperature, it shifts a little bit to the right in this way. Now, and the next one is we have subcooling of the condenser exit. So in the the previous cycle, the fluid normally is cooled from superheated state up to saturated liquid state. But here in actual cycles, the fluid is further cooled into this is what we call subcooled state. You understand? Subcooled state, because before eventually the fluid is throttled back to state 4. So there is a gap over here. There is a small temperature change between the previous one, which is state 3, and this. Yes, so we will look at cascade refrigeration cycle. So the word cascade means that if you have, let's say, 2 or 3 or more refrigerators that are mounted one on the other, okay? The purpose of this cascade refrigeration cycle is to increase the efficiency or increase the COP of the refrigeration cycle. Or in other words, let's say if you need a very, 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 very low temperature refrigeration compartment, then you need to use the cascade refrigeration cycle. So the word cascade means you have 2 or 3 refrigerators that have been mounted on one another, okay, performing the same job. So this is commonly used in industrial application, okay? And then large temperature difference requires a large pressure difference. Compressors have low efficiencies for large pressure difference. They result in low system efficiency. Okay, so the refrigeration cycle is performed in stages. Okay, yes, so this is an example of the cascade refrigeration cycle. This is a clear example. So let's say we have refrigerator number 1. Okay, now refrigerator A or refrigerator number 1. So what happened in this refrigerator is that, let's start with the B part first. Okay, in the B part, heat is taken from the refrigerated space into the evaporator. Okay, so what I mean by this heat being taken into the evaporator is that the temperature of the fluid over here at state 4 is much, much lower than the temperature. I'll say this is TL. You understand me? So T4 is much, much lower than TL. This means TL is high. Okay? So when the fluid enters this region, it will be absorbing the heat from here. So in other words, its temperature will be increasing gradually until it exits at state 1. Okay, so during that state, we follow this trend. It goes like this, state 4. So fluid is being heated up, so more vapor is forming, you understand me? Until when eventually the fluid is now saturated vapor, then it exits at state 1. So at this state, the fluid is compressed by the compressor. So there is compression, isentropically compressed. Okay? Then eventually it enters this condenser. So now there will be cooling. Condenser means that there will be heat rejected. You understand me? So now from state 2, it goes on to state 3. So it means the fluid is cooled right to saturated liquid state in this way. And then again, it enters the throttle valve, then there will be expansion in this way. Now, if we look at this, the second, the top refrigerator, so here, again, at state 8, the fluid enters the evaporator. Okay? So what is happening over here is that the temperature, again, the temperature at state 8 is much, much lower than the temperature over here. You understand me? So let's say the temperature over here is AB. So this temperature, TAB, is much greater. So there will be heat rejected. There will be a potential for heat rejection into this particular evaporator. You understand me? So it means that the heat will be rejected, and then gradually the fluid will be moving to state 5 at saturated liquid, saturated vapor state, before eventually it is compressed again. Okay, slowly it is compressed to superheated state at state 6. So then before again it is throttled. Oh, sorry, the heat is rejected, means there is cooling. Cooling is taking place, QH is being rejected to the surrounding. So then the fluid goes to state 7 before eventually it is again throttled down at this evaporator. Oh, sorry, at the throttle valve section, it throttles down to state 8. And then the cycle continues like this. You understand? Okay, so this is the basic operation for the throttle refrigeration cycle. So now if you look at if you apply the first law, okay, of thermodynamics to this system, then what we will observe over here is like this. So we will discover that the amount of energy which is being released by, let's say, refrigerator B. You see, this is releasing some amount of heat, and the refrigerator A is absorbing the heat. Okay, so that the total amount of energy released by this will be equal to the amount of energy absorbed by this refrigerator. So that's what we have written over here. So the amount of energy absorbed, by refrigerator A equals to the amount of energy released by refrigerator B. So the ratio of their mass flow rate gives us the ratio of this enthalpy. Similarly, now the COP for the refrigerator is given by, we know classically, COP for a refrigerator equals to QL divided by WE. Okay, so now this QL means both refrigerators, A and B, okay, they are all working together in order to maintain this refrigerator space at a lower temperature. So it means it is a combined effect of compressor B and compressor A. You understand? So now this gives us the COP equals to QL divided by W net. The W net equals to the work done by compressor A plus the work of the compressor B. Okay. Now this is an example of the cascade, okay, refrigeration cycle, okay, where a temperature at a very, very low temperature is desired in a reactor. Okay, so this is the cascade refrigeration cycle, and then we have the reactor over here. Okay, so the heat, the temperature, because of this low temperature which is required, we have to use a cascade refrigeration cycle to maintain that. So this is the general overview for the cascade refrigeration cycle. See, so it's a very important. So this refrigeration, you can say, let me see, refrigerator A, this could be B, this could be C, and keeps on going up, up, up like that. Okay, so eventually they are all working to reduce the temperature of the refrigeration space. Okay, so you see this has its own compressor. This is a low pressure compressor, and then we have high pressure compressor over here. And then they could be working on different refrigerant as well. You understand? Okay. Also, this is a typical example. So you see, and yes, so now the last part, we have multi-stage compression. Multi-stage compression refrigeration cycle. This is done in 2 stages with a mixing chamber in between them. Okay, so this is similar to cascade. So the only difference is that we have a mixing chamber in between the 2 refrigerators. See this refrigerator number 1, this refrigerator number 2, and we have a flash chamber in between them. So again, let's see what happens over here. First, the refrigerant from state 8 enters the evaporator. So on the TS diagram, it goes on up to state 1. Then again, the fluid is compressed in the first compressor. Then it enters this mixing chamber. Okay, so this mixing chamber means this is a cold fluid. State 3, the line at state 3 is a cold fluid, and this is a hot fluid. So the moment it mixes with this, T2 and T3 mix, immediately the temperature of T2 is going to drop all the way up to state 9. Okay, so now the fluid at state 9 is still in the superheated state, and then it enters the second compressor. So then the fluid is compressed to again high temperature before eventually the heat is released to the surrounding, and then the fluid is cooled down to state 5. Then eventually we have expansion at state 6. Okay, so then the cycle continues like that. Okay, but again over here at state 6, the fluid that enters at state 6 is saturated liquid vapor mixture. So the liquid goes to state 7 and the vapor goes to state 3. You understand me? So that's the significance of this particular mixing chamber. Okay, so after the first expansion, a liquid vapor mixture is present. In a flash chamber, the saturated vapor is removed and sent to the mixing chamber, while the liquid goes through the second expansion valve, like this. Okay, so let's see. So all these things are not necessary. Okay, important questions, I will discuss them later on. So application of refrigeration. So the application of refrigeration is in the food processing industry, preservation, okay, and distribution. Okay, so in our big malls, on cold store, okay, where they have ice blocks, okay, for let's say pharmaceutical companies, okay, or the fish industries, okay, so all these applications can be found in the fish industry, poultry, fruit, okay, dairy, and so on and so forth. Okay, so the temperature range for each is given like this. Then application of refrigeration in chemical and process industry, the separation of gases, okay, condensation, solidification of solids, okay, and then removal of heat, exothermic reactions, and recovery of solvent, like this. And then we have domestic refrigeration, air conditioning also. See, this is a basic refrigeration cycle. So this is a domestic refrigerator. So almost every household in Malaysia have a refrigerator. So this is the basic component of a refrigerator. And then also its application also in the air conditioning. So air conditioning, almost every house has air conditioning. Okay, later on, when we look at air conditioning processes, then you will come to understand the relationship, how refrigerators and air conditioners are connected. And the assignment that has been given to you, okay, so, and these applications are found over there. So I think it is a bit too early for you to start worrying about how to solve this question. Okay, that is the assignment. So I'll find some time, perhaps next week, to explain in general to you how to handle this assignment. Okay, so we need to finish especially refrigerators and then air conditioning. Okay, so before we will be able to complete the assignment. And if there is a need for me to extend a little bit, I think I will do that. Okay, so also in chillers and cold room also. Okay, we have seen this diagram already. Okay, and this is air conditioning. Okay, so this particular part I'm going to attend to it next week. Okay, so probably I'll solve one question, okay, before we leave today, and then next week I'll solve some more questions, but next week I'm going to start with air conditioning, okay, because we don't have much time. I need to cover air conditioning and convection, at least before the end of the semester. Okay, so, and I will, let me see, try to solve some questions. So far, is there any question regarding the slides? If there is any question, let me know. Yes, so let's see. Maybe I will start with this question. Yes, so let me see. Maybe I'll start with this particular question first. So I don't know if you have your property tables with you. I may need your assistant, okay, to use the property table. So I want to use these slides. So wait there, I'm coming. I'm just trying a way to insert text. Okay. Okay, so what I'll do is I'll copy this and put on. So I'm trying to set up the question. Okay. Yes, so sorry for the delay. Okay, so the question has just appeared. Here we are told that a refrigerator uses refrigerant. Quickly, I'll just discuss this question, okay, how you can handle it. We are told that a refrigerator uses refrigerant 134A as the working fluid. The refrigerant enters the compressor. Okay, so quickly we can sketch our refrigeration cycle like this. Okay, so in every refrigerator, we have this is the compressor. Okay, we have the throttle valve, and then we have the evaporator like this. Okay, so here we have the refrigeration compartment, and then we have the surrounding. So this is QL, this is QH, okay, and then here we have W in for the compressor. This is W in, this is QAL, this is QH. All right, so let's say this is state 1, state 2, state 3, and state 4. Okay, so this is evaporator. Sorry, we have evaporator over here. So we have evaporator here. Evaporator is this. And we are told the refrigerant enters the compressor at, so it means that P1 equals to 0.14 megapascal, and T1 equals to minus 10 degrees Celsius, and is compressed to 0.7. So it means P2 equals to 0.7 megapascal, and T2 equals to 50 degrees Celsius. The refrigerant is then cooled in the condenser. You understand? In the condenser to a pressure of 0.65 megapascal. And then T3 is this, P3 is this, T3 is also 24 degrees Celsius. And it's throttled to it's throttled to 0. So it means P4, 0.14 megapascal. And the mass flow rate of the refrigerant is given. Mass flow rate equals to 0.12 kilogram per second. Okay, 1.2 kilogram per second. Now, determine the rate of heat removal from the refrigerator space. So in this case, what are we supposed to calculate? And then the work input to the compressor. You see, very clearly, we are told to determine the rate of heat removal. Rate of heat removal from the refrigerator space means we want to find QL. And also the rate of heat input, and the power input to the compressor. So we want to find W in also, which we don't know. Okay, so clearly we have to sketch the TS diagram for this particular cycle. Let us draw the TS diagram for this cycle. So okay. So basically, in every refrigeration cycle, okay, so we have the low pressure line, which is given by this. Okay, so initially, we are told that the fluid enters the compressor at 0.14 megapascal and minus 10 degrees Celsius. So we are going to assume that the input at state 1 is, this is state 1. Means this constant pressure line, this is P1. So what are the properties of the fluid here? It is 0.14 megapascal. And T1 equals to minus 10 degrees Celsius. Be careful over here. You have to be extra careful. So here we don't know whether the fluid is actually at superheated state or at saturated liquid, saturated vapor state. So you cannot conclude like this just by saying that it could be that the fluid is in the superheated state. It means this particular state is going to be state 1. You understand me? So how do you determine that? We need to find T saturation at the given pressure. Then we'll compare with this temperature. You understand? So it means that at state 1, let's see over here, at state 1, okay, T saturation at P equals to 0.14 megapascal. That gives us what? What is the saturation temperature? Can anybody help us with this? So this gives us the pressure will be 140 kilopascal. Okay, T saturation, so T saturation at 140 kilopascal. So what will be the value? So let me see if I have this. Okay. So if somebody can help me with on the property table, T saturation, you go to refrigerant 134A, and then under pressure column 140, what is there? Corresponding saturation pressure. So here, let me see. So saturation temperature is this. Saturation pressure. Yes, saturation pressure at 140 kilopascal. 140. Let's see over here. So we have 150 over here. So refrigerant 134A. For refrigerant 134A. This is for, yes. Yes, at 140 kilopascal, I got the temperature to be minus 18.7. So I got a temperature to be minus T saturation to be minus 17 point. Let's see. So this gives me 18 minus 18.77. So, but the temperature which is given to us is minus 10 degrees Celsius. So you see, T1 is what? Greater than T saturation. You understand? So this means that our fluid is not at a saturated liquid state. It is at a superheated state. You understand me? So here, T1, since T1, okay, is greater than T saturation, because minus 10 is greater than minus 18. Minus 18 is at much lower temperature. You understand me? So minus 10 is greater than minus 18. So now we will have, so this implies that, this is very important, please, because if you make a mistake and you say, oh, the fluid is in the saturated vapor state, so then again, all your solution will be, null and void. You understand? So you have to be very, very careful. So here we will have, since T1 is greater than T saturation, this implies state 1. State 1 is what? Saturated, superheated state. Superheated state. So it means that if you have to determine all properties at state 1, then you have to go to the superheated state like this. Very, very important. Okay, so it means if you have to look for H1, you have to find S1, then specific volume V1, all you have to refer to the superheated state, the superheated table. So clearly we go to the superheated table at 140 kilopascal and the given temperature, minus 10. Okay, so we will determine this, all these parameters at P1, 140 kilopascal, and T1 minus 10 degrees Celsius. Okay, so now if you go to the property table, I hope you have your property tables with you. If not, then it's a bit difficult for you like this. So we go to the property table, and the superheated table states still refrigerant 1348. So we look for 0.14. 0.14, yes, 0.14 is there. And then minus 10 degrees Celsius. So minus 10 degrees Celsius. So all the properties are given. We have the internal energy, we have the specific volume, we have the enthalpy, we have the entropy. Very clear. Okay, like this. Okay, so let me see. So the enthalpy and entropy are this. So let me see. Yes, so this is the enthalpy. So the entropy is this. And then the enthalpy S1, sorry, H1 is given by this. So that is H1. H1 is given by this. And then specific volume V1 also is this. 0.14. So specific volume is this. So we may not be able to complete this question today. We may have to again continue again some other time. So this is the specific volume. The specific volume is this. Okay, so let me add a unit. This is kilojoules. Kilojoules per kilogram, per kilogram. And then this is also kilojoules. Kilojoules per kilogram per Kelvin. Okay, per Kelvin. And this is meter cube per kilogram per kg, kilogram. Right? So these are very important properties. So now, according to this diagram now, the fluid starts at state 1. So gradually it goes up. So now we will have our high pressure line to be this. So it continues upwards like this. Okay, so now let us look at state 2. What are the properties of the fluid at state 2? We are told that the refrigerant then cooled in the condenser. And the refrigerant enters the compressor at 0.14 and minus 10 and is compressed to 0.7 and then 50 degrees Celsius. So it means that this state 2 Okay, this state 2. So P2 equals to 0.7 megapascal, and T2 also equals to 50 degrees Celsius. So there is no doubt that this state is always superheated. State 2 is always superheated. So there is no even for you to confirm whether it is superheated or saturated vapor state. It is all the time in the superheated state. Okay, so all that you need to do is just to find the enthalpies and then the properties of the fluid at that state. So that at state 2, we'll have P2 equals to 0.7, yes, 0.70 degrees Celsius. So that gives us 700 kilopascal, and T2 equals to 50 degrees Celsius. So now with this, let's find the entropy at state 2 and then the entropy at state 2. Okay, so now we will go to the property table again at 0.7 and 0.7. Let me see over here, where is it? So 0.6, yes, 0.7 is there, and 50 degrees Celsius. So 0.7 and 50 degrees Celsius, it is given by, I hope you know how to do these things. Maybe I should show, let me show you the slide. Okay, let me show you the slide on this. Just 1 minute. So I'm downloading the soft copy for this property table. Let's see. Yes, so this is the property table which I was looking at. See, we are talking about this temperature. Okay, so saturation, this is for water. So for refrigerant, we are now for refrigerant. This is refrigerant 134A. Okay, so, and then these are its properties. So at the superheated state, 0.7, here is it, 0.7, and then at 50 degrees Celsius. What are the properties? The properties are this. Please, next time you bring this property table with you, and then you can help me to read. So then we can proceed very fast, like this. Okay? So here, according to this property table, now let's continue with the solution of this question. We will have this. From this property table now, we will have, yes, the enthalpy and then the entropies are given. So according to the table, we have at 0.7 and 50 degrees Celsius, enthalpy and entropy are given by, so we have 288.53, 288.53 for the enthalpy. So here we have 288.53, and then the entropy is also given by 0.9954. 0.9954. So this equals to 0.9954. This is kilojoules per kilogram. So kilojoules per kilogram per Kelvin. So quickly, then again, the question goes on to say that now the refrigerant is then cooled in the condenser to 0.65 megapascal and 24 degrees Celsius. So the pressure over here, you see, the pressure over here is 0.7. But we are told that during the cooling process, the pressure was reduced. So it means that it goes like this. The actual reduction goes like this. And then it goes this way. Okay? So this is the actual situation. And then let's say this is state 3, but we cannot tell. So at this particular state, the property of the fluid at state 3, we are told is 0.65 pressure and 24 degrees Celsius. So we have to cross-check whether it is the fluid is in the saturated liquid state or is in the compressed liquid state. We have to decide. So how do we determine that? Again, we need to find, we know P3, 0.65 megapascal, which equals to 650 kilopascal, and then T3, 24 degrees Celsius. So let us find T saturation at 650 kilopascal. How much is that? So if you do this at 650 kilopascal, means 0.65, okay, pressure for on the property table, we will have pressure table is there. Pressure table. So 650 temperature is saturation temperature 24.20. See, very clear. Okay, temperature is equal to 24.20 degrees Celsius. So what does that mean? So it means that T saturation or T3 is less than T3 is less than T saturation at what? 650 kilopascal. So which means this fluid is in the compressed liquid state. You understand? So it implies state 3. State 3 is compressed liquid. Understand? So if it is compressed liquid state, then how do we determine the properties, the enthalpy, the entropy at state 3? So it means on the TS diagram, we will have the fluid is going to be at this state, not this. So our state 3 is going to be here, state 3, in the compressed liquid state. Okay, so before eventually the fluid will be throttled back to state 4. And even at this state 4, what is the pressure? The pressure at state 4 is 0.14, okay, megapascal. So, and which is clearly the same as the pressure at this particular state. So it means P1 is the same as P4. Okay, so now we'll stop very soon, okay, because I have another discussion at 6:15, and I need to make my Asar Salat before I will join that discussion. Okay, so let me just show you how you are going to handle this question. So now what you have to do is that we need to determine the enthalpy, H3, okay, and then S3 at compressed liquid. But you see, at the compressed liquid state, there is no, we do not have properties for the refrigerant. Okay, there are no properties for refrigerants at compressed liquid state. You will never find it in a property table at a compressed liquid state. So we will make a very good assumption. So therefore, we assume that the fluid is at the saturated what? Liquid state. At the saturated liquid state. So therefore, H3 is going to give us H4 at the given temperature, not pressure, at the given temperature at T3. You understand me? So that's how we're going to determine that. Okay, so means which T3 equals to 24 degrees Celsius. Okay, so now I've told you all the information necessary to determine all the properties at each state. So next thing to do is to determine, we want to find, what do you call it? The rate of heat removal, QL. So what is the definition for QL? So this I'm not going to do, I'll just explain to you. So QL is given by mass flow rate into bracket H1 minus what? H2. Simple as that. So H1 we know already, H2 we know already. So therefore you can easily determine the QL. You know the mass flow rate already. So very easy. Similarly, we have to determine W in equals to mass flow rate. So H2 minus H1. Oh, sorry. H2 minus, let's see what was the notation for that. Oh, sorry. This supposed to be, I'm very sorry. This supposed to be H1 minus what? H4. H4. Be very careful. Okay, so for the evaporator, because here, look over here, we have the fluid is entering over here, and this is state 4, and this fluid is leaving, this is state 1. That's for this one. And then we have QL, which is this. You understand me? Okay, so it's going to be H1 minus H4. So now your problem is, how do you determine H4? Yes, so very easy to determine H4. I've told you that, yes, so let me complete this H2 minus H1. How do we determine H4? So I've told you H3 is the same as H4. You understand? For all throttle valve, H3 is the same as H4. So it's very easy. So it's very difficult to determine H4 here. But the moment you find your H3, then it will be the same as H4. Okay, so that's the easiest way by which you can determine your H4. So also over here, H1, H2 already, you know already like this. So you can easily calculate. Okay, so then next, to determine the rate of heat rejection to the environment. Okay, so how do we determine the rate of heat rejection? When we say rate of heat rejection to the environment, that is QH. We want to calculate QH. So that's it. So very easy. Now, all that you need to do is to write down the energy balance for the refrigerator. Okay, so here is the refrigeration space. Okay, so here you have you have W in, you have QH, and you have QL. So if you find the energy balance, you see QL is going in, W in is coming in, and this is going out. So we will have W in plus QL equals to, QL equals to QH. You understand? So it means that if you already know W in and you know QL, so you can easily calculate your QH. So this is the simplest way by which you can calculate your QH equals to W in plus QL. You understand? Okay, so then the coefficient, COP, coefficient of performance for the refrigerator equals to QL divided by W in. That's all. Okay, so this is the solution to this particular question. Okay, so anybody has any question so far before we stop over here? Is there any question so far, please? Yes, so any question so far? No question. All right. So then it means we will stop our discussion over here.